So let's go ahead and find a formula for the sum of the first n perfect squares. We're going to start by defining a sequence, a counting sequence of the perfect squares. We'll denote it a sub n. Okay, so here we got 1, 4, 9, 16, 25, 36, so on and so forth, right? Okay, don't have to put too many in these in here, but enough so that we can describe a pattern developing when we consider the sequence of partial sums. So the sequence of partial sums, first sum is 1, and then it's going to be 1 plus 4, which is 5. That plus 9, which is 14. That plus 16, which is 30. That plus 25, which is 55. That plus 36, 91, took me a second there. That plus 49, which is clearly 140. And that plus 64, which is going to be 204, and on and so on. Now, we want to again identify, if you've seen some of these other videos regarding finding the formulas, okay, you can recall that we want to find constant differences. If you have a constant first difference, you've got a linear growth pattern. If you have a constant second difference, a quadratic growth pattern. Constant third difference, a cubic. Constant fourth difference, a quartic, so on and so forth. Okay, it's kind of a process of mathematical induction in reverse. We're noticing a pattern, and then we're building our statement based on the observation of that pattern. So clearly we are going to add 4 here. We're going to add 9 here. 16, 25, 36, 49, and 64. Okay, so we don't have a constant first difference. It'd be kind of surprising if we did. We know this is not a linear growth pattern. This is certainly not a linear growth pattern, therefore. Okay, so how do you get to 9 from 4? We have to add 5. To get to 16 from 9, you add 7. To get to 25 from 16, you add 9. To get to 36 from 25, you add 11. Here we can see we add 13. Here we add 15, and so on and so forth. Okay, so we don't have a constant second difference either, which means we're not looking at a quadratic growth pattern. But if you take a look here in the third iteration of this method, you can see that we do have a constant difference. 2 is being added each time. Okay, which means we've got a cubic growth pattern. So a constant third difference means a cubic relationship is present. Okay, and so we can typify that by S sub n equals an cubed plus bn squared plus cn plus d. Okay, let's go ahead and zoom out one step there, give us a little bit more working room. Okay, so we got 4 unknowns that we need to find, a, b, c, and d, but we got plenty of data to do that. Okay, I know that when n is 1, S sub n is 1. When n is 2, S sub n is 5. When n is 3, S sub n is 14. When n is 4, S sub n is 30. And I don't really need to go beyond that because I know if I have 4 equations and 4 unknowns, I can solve that system. Okay, let's go ahead and set up the system. So a times 1 cubed plus b times 1 squared plus c times 1 plus d is equal to 1. Okay, good. So the first partial sum is 1, and the second partial sum we know is 5. So let's do that. Okay, second partial sum. okay, which we know is going to be 5. Okay, third partial sum we know is 14. Okay, third partial sum. Let's get that established. We know is 14. And then the fourth partial sum we know is going to be 30. Okay. Fourth partial sum we know is going to be 30. Okay. So we got this system here. And we want to go ahead and simplify it. Okay. So this is going to give us A plus B plus C plus D equals 1. 8A plus 4B plus 2C plus D is equal to 5. Okay, 27A plus 9B plus 3C plus D is equal to 14. Okay, 64A plus 16B plus 4C plus D is equal to 30. Okay, I think we should probably zoom out one step here. Maybe even one more step, huh? There we go. Give us a lot more working room there. Okay, so let's check our work, make sure we haven't made any critical mistakes before we proceed. Looks pretty good to me. Indeed, it is good. Okay. 1, 1, 2, 5, 3, 14, 4, 30. Yeah, it looks good to me. Okay. So notice that we have a freestanding D here for all. So it's almost kind of screaming at me to just solve each one of these for D and then set D equal to D 3 times. Okay. That eliminates a D. That's going to give us a 3 by 3 system, right? 3 equations, 3 unknowns with A, B, and C. Okay, and that'll simplify things dramatically. So let's do that. Rather have a 3 by 3 than a 4 by 4 system. Okay, so here solving for D, we're going to have D equals 1 minus A minus B minus C. Here we're going to have D is equal to 5 minus 8A minus 4B minus 2C. Here we're going to have D is equal to 14 minus 27A minus 9B minus 3C. And here we're going to have D is equal to 30 minus 64A minus 16B minus 4C. Okay, let's check that, make sure no critical errors there. Okay, looks like we don't have any. Looks like we've done our mathematics correctly. Okay, and now let's, as I said, set D equal to D equal to D equal to D. Okay, so we're going to have 3 equations now, not 4, since the D's are going to become irrelevant. It's going to help us out a lot. So the upper and the second one, the first and the second equations can be set equal to each other. So we got 1 minus A minus B minus C is equal to 5 minus 8A minus 4B minus 2C. Okay, I can then set the second equal to the third. Okay, so it's going to give me 5 minus 8A minus 4B minus 2C is equal to 14 minus 27A minus 9B minus 3C. And then the third equal to the fourth, we're going to have 14 minus 27A minus 9B minus 3C is equal to 30 minus 64A minus 16B minus 4C. Okay. Let's take a close look at that, make sure there are no errors on the page. Don't think there are, but again, got to be careful. Mistakes can crop up at any time. Okay, just checked it. It looks good. Let's now, well, what are we going to do here? Let's think about it. We are going to go ahead and, if I add 2C, add 3C, add 4C to the first, second, and third, both sides of the first, second, and third equations respectively, I'll be able to actually solve for C for each one. So I'm going to actually solve for C now for for all three of these equations rather. So top equation, okay, adding 2c to both sides, negative c plus 2c is c. Okay, we're going to now subtract 1 from both sides. We're going to add a to both sides, and we're going to add b to both sides. And there's our new top equation. Okay. Second equation, okay, let's add 3c to both sides. Negative 2c plus 3c is c. Subtracting 5 from both sides. Adding 8a to both sides. Okay. Adding 4b to both sides. Okay. And then with the third equation, let's add 4c to both sides. And we get negative 3c plus 4c is c. Okay, now we subtract 14 from both sides. Add 27 to both sides. Okay. Adding 9b to both sides. Okay. That's a lot cleaner to look at than this. I don't know about you, but I prefer this. Let's take a look, carefully make sure that we have made no mistakes. No mistakes, okay? First equation looks good. Let's take a look at the second equation. Okay, subtracting 5, adding 8a, good, adding 4b, good. And then, of course, the third equation, let's check that quickly, adding 4c to both sides, subtracting 14 from both sides, good, adding 27a to both sides. Yes, negative 37a is going to be the result of that. And then adding 9b to both sides, negative 16b plus 9b is indeed going to be negative 7b. Well, now we find ourselves in a very similar set of circumstances to what we found ourselves in right here. A very convenient set of circumstances, I should say. We can now set c equal to c and c equal to c, thereby eliminating c and reducing this to a 2-by-2 system, 2 equations, 2 unknowns. That's what we want. Okay, so setting the top equation equal to the middle equation, we're going to have 4 minus 7a minus 3b, okay, is equal to 9 minus 19a minus 5b. Okay, and then we've got the middle equal to the bottom, so 9 minus 19a minus 5b is equal to 16 minus 37a minus 7b. Okay, good. Let's check that. Not necessary to check it too deeply, just copying things down, but yes, that looks good. Okay, now looks like if I add 5b to both sides, I'm going to have 2b here. If I add 7b to both sides in the bottom equation, I'm also going to have 2b. So that's convenient. Let's just solve for 2b for both, and then we can set 2b equal to 2b and thereby solve for a. Okay, now you could use another system, another method for solving this, including elimination or substitution, or you can even use matrices or even Cramer's rule. But again, there's really no need to do anything so heavy-handed. This system of equation lends itself to this very convenient method that I'm using here. So hopefully you find that helpful. Okay, again, adding 5b to both sides of the top equation and subtracting 4 from both sides, adding 7a to both sides. Okay, good. Now, bottom equation, let's add 7b to both sides. Negative 5b plus 7b is 2b. Subtracting 9 from both sides. Adding 19a to both sides. Okay, let's check that. Make sure we haven't committed any flaws. Yeah, looks good. And 7, add 19a. Negative 18a. Yeah, that's correct. So, what do we got? Well, this is what the moment we've been waiting for, right? We got 5 minus 12a equals 7 minus 18a. Okay, good. Let's add 18a to both sides and subtract 5 from both sides. So negative 12a plus 18a is going to be 6a. 7 minus 5, of course, is going to be 2. So we know here that a equals a third. Okay. Well, now that we know a equals a third, we can definitely go ahead and find b. Okay, so we'll just do that right here. Using this equation right here, we're going to have 2b is equal to 5 minus 12 times a third. Okay, we can zoom out one more step, I think, here. Just one step. There we go. So that's going to give us 5 minus 4, because 12 divided by 3 is just 4, and that's just 1. And that means, of course, that b equals 1/2. Got to divide both sides by 2 there. Okay, good. One step closer. Let's now find c. I'm going to go ahead and just use this top equation. I like the coefficients. They're a little bit smaller than these ones. Well, not smaller as in smaller, but as in easier to work with. How about that? C. Okay, what do we got? We got 4 minus 7a, which is 1/3, minus 3b, which is 1/2. Okay, so plugging those values in there. Now, we're going to have 4 minus 7/3 minus 3/2. Now, all these have a common denominator of 6. So we're going to go ahead and multiply top and bottom by 6 here. So we get 24/6. Put 6 over under everything. Top and bottom here, we're going to multiply by 2. Top and bottom here, multiply by 3. All over 6. Okay, so 24 minus 14 is 10. 10 minus 9 is 1. So C is equal to 1/6. Okay, now let's go ahead and find D. Well, D, just use this top equation again. Easier coefficients to deal with. D is equal to 1 minus A minus B minus C. Okay, and this is just 0, I guess, right? Yeah, so 6/6 minus 2/6 is 4/6, and 4/6 minus 3/6 is 1/6, and 1/6 minus 1/6 is just 0. So we are done. We found it. So S sub n is equal to 1/3 n to the power of 3. Okay, good. Plus 1/2 n squared. Good. Plus 1/6 n. There you have it. Okay, good. Now, I think it's typically the case we want to write this as a factored, well, not always, but I think for the summation formula that we use in calculus when we're studying those Riemann sums and applying the limit definition of the integral to find areas, right? So we can really understand not just the how of integration, but the why of integration. We use those factored forms, okay? So we can actually go ahead and take an n over 6 out of everything. And then what's left? Well, I'll just put the 6 over everything. So it's going to be n, and then what's left if I take an n out? It's going to be n plus 1, 2n plus 1. There we go. All over 6. That's what I'm going to be putting a box around, because that, well, we'll put a box around everything. Okay, this will work out in just a second. Right. There we go. Now, a little bit of work. Not so bad, though, right? This is actually one of the more reliable formulas, or one of the formulas, I should say, that we rely on more later on when we study calculus and then, of course, real analysis. Essentially, what we're doing here is introductory real analysis, right? We're using kind of reverse induction techniques to find these patterns and these formulas, which, by the way, come in handy. Many of the later statements require a knowledge of these, and the Bernoulli numbers, of course, which are determined by the constants that arise in these the lowest powered coefficient, which arises, can also be described, and those indeed are extremely helpful for finding the the series expansions of many different transcendental functions. That's much later on, though. Let's not get ahead of ourselves. Hopefully you found this video to be extremely interesting. Again, we love mathematics around here. We love physics. We love anything that requires analysis, and we will anticipate receiving questions and problem propositions so that we can solve, rather prove and derive different statements. It's our goal to derive everything and prove everything at some point that we can. And what the time is remaining and that which is humanly possible to do. Have a great rest of your day, and thanks for watching.